Hi everyone, this is Qiang. Today I will talk about 300 ampere single stage 40-volt voltage regulator with multiphase current Doppler rectifier and the integrated transformer. With the development of microprocessor, the current required increases very fast. For CPU application, it will require more than 300 ampere current, and for GPU application, the current is even higher for more than 600 ampere. With the increased current level, the VR design becomes more challenging to achieve the goals of high current, high efficiency, and high power density. To achieve the design goal, a single-stage 40-volt solution gets our attention. The solution utilizes the half bridge for the primary side and the current Doppler rectifier for the secondary side. Compared with state-of-the-art two-stage solution, the solution is so simple and the device number can be reduced significantly. From the operating waveform, it can be observed that the control is very simple, similar to a two-phase buck converter. However, in TI solution, the discrete inductors are used and the power density is only 150 watt per inch cube. In order to further improve the power density, we found an integrated magnetics for current Doppler rectifier, which is proposed by Dr. Peng Xu from CPAS in 2002. Here is a conventional current Doppler rectifier with one transformer and two discrete inductors. First, the position of the SR and the inductors are changed. Then, split the transformer to two transformers. Here, we can observe the middle point of these two transformers is floating. Then we can clamp the voltage of it to the output voltage by connecting the D and D prime point. Since the two transformer is in series, then the ID equals to 0, and the operation of the current Doppler rectifier is not changed. From the circuit diagram, it's not difficult to find. The output inductor can be seen as the magnetizing inductance of these two transformers. As a result, we can use two UI core to integrate the output inductors into the transformers with the magnetizing inductance. Besides, the two UI cores can be merged into an EI core, and the flux can be designed to have the direction as shown here. Then we can introduce some air gap in the center leg to create two additional flux passes. Since the two flux will cancel with each other in the outer leg, the two inductors are negative coupled. Dr. Peng Xu used the structure to build a converter for 400-volt input and 40-volt output. However, for VR application, the current level will be 100 ampere. For single current Doppler rectifier, it's impossible to provide such large current, and the multiphase current Doppler rectifiers are required. Here, we proposed a further integration method, one for two current Doppler rectifiers. Here shows two EI core and the two current Doppler rectifiers. First, the two plates of the EI core can be merged. Then we can also merge the center leg into a larger center leg. In this way, all the four inductors are negative coupled. However, when simulate it in 3D FEA tool, first we find from the flux distribution in the core, most of the flux comes from the outer leg to the in the core. Most of the flux comes from the outer leg to the center leg, and the two areas are not well utilized. In addition, with negative coupled, the DC flux of the center leg is the sum of the four outer legs, so the center legs are larger than the outer legs. Then the center leg will take the space for the winding And from the current density, the narrow winding around the center lag will lead to larger winding loss. Also, there are several areas with small current density. For this structure, we want to integrate the SR and the output capacitors into the winding to reduce the termination loss. So only two areas can be used, and these two areas can match well with the two areas in the flux distribution. Finally, we find the two corner areas that can be used to reduce both winding loss and core loss. The idea is to separate the center lag into three pieces using the corner areas as shown here. After splitting the center lags to three pieces, the flux distribution in core is more uniform with two additional flux passes, and there is no current clouding because the lags are smaller. Finally, the total loss can be reduced for 22% with the separate center lags. Except the integration 1, the cores can be reorganized at the integration 2. Since now the center lags that do not take additional space, the two methods have similar footprint. We are applying for a patent for this structure. For the method 1, the four outputs are symmetrical, and the steady state inductance are the same. For the method 2, with unsymmetrical structure, the steady state inductance have about 10% difference. However, the outputs of integration 1 are at the top and bottom, which will have a longer path to the load under the steady state state-of-art microprocessor method for motherboard design. From this point, the integration 2 suits the state-of-art XPUs better. Here shows a hardware prototype of the proposed integrated multiphase current double rectifier. The prototype is designed for a continuous current of 160 ampere and a peak current of 300 ampere, which is defined for a short period of time. The prototype sets a new record for VR power density. Considering the 300 ampere peak current, the power density is 1.9 kilowatt per inch cube. And if we only clear the footprint, the power density is 330 watt per inch square. Here shows operating waveform under the 300 ampere peak current. Since now we operate it under hard switching, it creates the voltage draining and brings larger switching loss. And here shows the state-of-art 12-volt to 1-volt multiphase buck converter for CPU and the GPU application. Compared with the multiphase buck converter, the half-bridge current double rectifier, which is designed for 48-volt to 1.8-volt, has similar footprint to the 12-volt to 1.8-volt CPU VR. In addition, there are two parts which are used for SR gate drivers. For commercial products, it's easy to integrate the gate driver into the SR. Then the footprint can be further reduced to 43 mm times 21 mm. It means the footprint is even smaller than the 12-volt to 1.8-volt CPU VR and has potential to get close to the 12-volt to 1-volt GPU VR. The efficiency curve of integrated multiphase current double rectifier is shown here. The peak efficiency is 92.7% compared with STM and Google switch tank converter-based two-stage solution with 12-volt bus. The peak efficiency is similar, and compared with the LLC DCX-based two-stage solution with 6-volt bus, the peak efficiency is a little bit lower. In a summary, the magnetizing inductance is used for the integration of transformer and inductors in current double rectifiers. And the two magnetic integration methods are proposed utilizing the corner areas for center legs to improve the power density. And the experimental results show proposed single-stage 40-volt to 1-volt structure has similar footprint to a 12-volt to 1-volt multiphase buck converter and the comparable efficiency to state-of-art 40-volt solutions. In the future, first we will optimize the SR and transformer design to reduce the SR loss, secondary winding loss, and the termination loss. In addition, we will realize the control method for half-bridge current double rectifiers with integrated magnetics. Thank you.